So our next speaker will be Jon Morse, who's coming to us from Caltech, and also astronetics and other things that he has going on. He'll be talking about the opportunities here to now complement the background that Michelle has been giving us on the interferometry side of things. So take it away, Jon.
Okay, thank you. And I see. And thank you for that introduction on what interferometry is. I will give a talk that has no physics in it. It is more art, and it has some discussion of programmatic planning, etc. So I'm going to briefly say something about dust on the moon, which is like the thing that really hangs up people. And it's also understood that when we're talking about doing an interferometer on the moon is of a certain size, and we hope to make very large interferometers in the future that would be more like the LISA baselines of millions of kilometers and do amazing type of imaging. And so a lot of the impetus for this workshop and other efforts is to look at what are these first steps of getting off the ground into space. And so I'll talk a little bit about why the moon and then some of the programmatic considerations, and then looking at those capabilities that Gerard mentioned earlier that we're building up mostly through NASA but also international. So the primary attraction of the lunar surface is, of course, that it's a stable platform in vacuum. There'll be more data on seismic environment coming. There's a JPL seismometer on one of the payloads going. You're going to hear the acronym CLPS, which people pronounce CLIPS landers to the moon, robotic landers of modest scale. And those CLIPS landers are taking payloads to the lunar surface, and I'll show you a slide that has what the current manifest is. And we can plausibly look at using such capabilities, but then also much larger ones. We, of course, are building on, when you go to the moon and you do ground-based on the moon, you are building on the experience and the techniques we've gained from the terrestrial optical interferometers. And I want to point out that NASA's done a study already of unique science from the moon in the Artemis era that has astrophysics as part of it. So there's radio observatory things and I think some infrared telescope things, but also there's at least a section with an overview of UV optical interferometry from the moon. There are many, many challenges of being on the moon. People are working on them for a variety of applications, and this list here, getting mass to the surface, meaning landers. You have to have power and comms. You have to deal with the thermal environment, 1/6 gravity, mobility, the dust, etc. Everybody has to deal with that who's going to the moon. No matter whether it's science or some other infrastructure-related capability, you need to deal with all these things. We will look at what we need and maybe how we deal with that during the course of this workshop. And so I don't dwell too much on those. And we'll be looking at data from LRO, the Lunar Reconnaissance Orbiter, for example, which has temperature maps, et cetera. And it matters where the sun is, where your landing site is, and how you get your power. Our goal, and the whole reason we're even contemplating something like this, is what we'll call modest baseline optical interferometers that leverage the capabilities and infrastructure being developed by other programs. That's what makes this, what we'll say, is relatively affordable. So I just wanted to address this question. Is dust a showstopper for telescopes on the moon? There is a mindset in our community in astrophysics, and there is a prevalence of it even at NASA headquarters, that do not want telescopes on the moon. It is, in my opinion, grossly misguided. And what I'm pointing out here is that it doesn't even follow the facts. There have been demonstrations on the lunar surface that telescopes work fine. And just from your sensibility, you would know any mission. Just take recent robotic missions to the lunar surface that take pictures of like a rover from a lander or the lander from a rover. It's like cameras work fine on the lunar surface, but oh my God, as soon as you tilt up just a little bit, forget it. You know, don't go to the moon to do astronomy. And I just think the data is not even close to suggesting that the moon is a great place to do astronomy. And so I just briefly look at the Apollo 16 camera, and then the Chinese flew something called the Lunar Ultraviolet Telescope on their Chang'e 3 lander 10 years ago. So here is the Apollo 16 camera, which observed in the far ultraviolet. And let's see, it says up here it had two channels, one with and one without Lyman alpha in it. And so this was led by George Carruthers, who is shown here on the right. And this is the instrument which was taken on Apollo 16. So this is probably a photograph from roughly 1971 or 72. And here is the instrument on the lunar surface over there. So it was literally moved on the lunar surface by the astronauts, these astronauts who are supposedly very, very dirty, and you would never do that. But you can do that. You can have a telescope that looks out at the heavens, and it was basically pointed manually by the astronauts. And they did, took far UV images of Cygnus. This had a wide field of view camera, and so it was many degrees across. One of these paragraphs here it is right here, summarizing the field of view, a 20-degree field of view with about 2 arc-minute resolution. And these were the first images at those wavelengths from space, basically. And they also took pictures of the Earth and saw geocoronal emission. And in my opinion, there's great implications for determining whether exoplanets have oceans just by looking at geocoronal emission versus other wavelengths. And I recommend if you're a UV optical person doing space missions, go into the ADS abstract service and just look at Dr. Carruthers' list of publications from 1971 to 1976 or beyond. It's like he's inventing single-handedly IUE and then Hubble and then UVEX. He's addressing all these topics about interstellar medium absorption and UV emission from stars, et cetera. It's pretty amazing. On the descriptive paper about the instrument and its operations, he closes with this statement. This experiment demonstrates the utility of the electronic graphic. We should use that word more, right? This is a transition from photographic plates to having digital detectors, and so this is among the first, the electronic graphic technique in space astronomy, as well as the great potential of the lunar surface as a base for astronomical observations. So this is a person who has done it and says this is a great idea. And so I don't know why we're listening to people who don't have this experience when we think about it. Lunar Ultraviolet Telescope on Chang'e 3. Again, I'm just putting up some abstracts so that you know what it is, but here's a picture from the rover that it released looking back at the lander. And here's the LUT on the side over here. It was 13 centimeters in aperture, I believe. It sat here, and then it had a flat scan mirror. That's how it operated. And they had specific protocols as they went from day into night, and there might be some lunar dust levitation you have to deal with. They just closed up their little aperture door, and then sometime after sunrise, the next lunar day, they opened up. Chang'e 3 had a RTG on it, so they were able to do multi-lunar days. They didn't rely on just solar power. They had a power source that would keep them above survival temperatures during the 14-day lunar night. And so this paper, 18 months operation of lunar-based ultraviolet telescope, a highly stable photometric performance. So they just looked at bright stars at a minimum and showed that the photometry was consistent over roughly 2 years. I think it went well beyond 18 months. But they have done the experiment. They have shown that dust is not a problem. You have to mitigate, take it into account when you do your engineering and your CONOPS on the lunar surface, but it is in no way, shape, or form a showstopper for, in this case, near-ultraviolet astronomy. And they crow about themselves being the first, I think this is one of these, talking about being the first robotically controlled telescope. So some programmatic considerations. When we're here at the workshop thinking about exactly what we do, you have science goals and then you have an implementation. And implementations require resources. And the resources in NASA astrophysics, for example, are quantized. So the buckets that are probably most useful for us looking at what we would call scientifically impactful results are the Explorer missions. The SMEX and the MIDEX have roughly those cost caps. I believe that's without the rocket. And then we have the larger probes, which are strategic and sort of billion-dollar class, maybe a little more. And then the large strategic. I didn't call them flagship, but that's what most people call them. And I said greater than 2 billion. So Roman was 4.5-ish, something like that. JWST, of course, was 10-ish. Habitable Worlds Observatory is projected at 11-ish billion, very large. And so you have to think about what is it that we want to accomplish and kind of which bucket might we plausibly be able to fit in, because there are different time scales. The decadal surveys identify large and medium strategic missions. And so if you want to go on a probe or a large strategic mission, you're in line behind Habitable Worlds and the far IR and or X-ray probes that were part of the Astro 2020 recommendations. And so, if you were a probe class mission, you need Astro 2030 to recommend you be in the queue following the far IR X-ray probes. And so that's a time scale for organizing. They'll get going formally in roughly 2028 timeframe, and they'll start asking for white papers. And so you need your science goals, your mission concepts, and what you want to do in that time scale. And so that's a projected outcome for we in this community looking at what we want to accomplish, coming out with a report and then taking next steps. There's also, I called it open topic, but it means unconstrained science, essentially. You have Pioneers, which is annual, $20 million. It's difficult, but not impossible to contemplate a concept that would fit within that. Then you have SMEX and MIDEX, and we hope these are approximately the release dates. I said hopefully there, because we are in the maximum uncertainty this month. The election just happened. There's an incoming administration. We have no idea who's going to be running NASA on January 21st. It is very, very uncertain about where we're going and what we're doing. Plausibly, the Science Mission Directorate will continue its competed mission lines, and we know that the Explorer missions have high priority at astrophysics, and it's just going to be budget about how quickly they can release these. I personally am really aiming for something we could look at for the MIDEX timeframe. I believe that this is a big enough bucket of funding, even if it were trimmed back a little bit, like it was for the TESS round, when the budget was highly constrained. But in that time frame, it means between now and then, you've got 2 years to put something together that has, projections for technologies at TRL6, et cetera. And so you've got a lot of work to do between now and then to be ready to compete there. I also want to bring up the foundations, which we in the community should see as an active player. Of course, in the ground-based communities, this is second nature. Keck, one of the best examples of a forefront facility that's funded mostly by non-government money. And now the private foundations are looking at space experiments. And they're even looking at things that are in this price scale, sort of explorer class, and it's a matter of what they do. So schmidtsciences.org and Keck Foundation and Kavli and Simons, among others, and the Gordon and Betty Moore Foundation, are foundations that might plausibly be interested in something that has a lot of opportunity to be at the frontier of science. So now I'll jump into what's happening with Artemis. I chose this depiction. It's not necessarily an Artemis camp, which always has the habitats and things in it, but this is something you might say is somewhat more near term. It has astronauts out here with hammers and chisels, okay. And then you have a robotic rover, and then a pressurized rover, so that's your mobility aspects. And then you have these power, everybody's talking about having these, they call them power masts that kind of go up instead of going sideways. And they point at the sun and provide solar power. I don't quite know what this thing is back there, but let's pretend it's communications. And then they have large landers, which are lot more mass to the surface. So I don't know what's going to happen with this one. We'll see how that rings out. Here's Starship depicted on the moon. Here's Blue Origin's lander called Blue Moon depicted on the moon. So this is the Artemis 3 provider and 3 and 4. And then Blue Origin is Artemis 5 and maybe 6. But Blue Origin is planning to do a demo next year, robotic, uncrewed, to the surface of that big giant thing. And so that would be cool. And the idea is, can we leverage this kind of capability for what we're talking about? I put up the Artemis Accords. This is the latest, with Norway having just joined. It's 48 countries in there now, meaning that the effort is highly international, with roles and responsibilities for certain elements of Artemis program, the hardware program. But all these people are interested in participating in the mission to the lunar surface and beyond to Mars. So I think this is terrific. And it means, because we, again, in this community, ground-based and space-based, we're used to doing international contributions, and we should definitely do this. So we leverage the infrastructure to support the human and robotic sustained presence on the lunar surface. That's what makes it affordable. And then we should look at these paths for international participation, because we know that our colleagues in other countries are very interested. This is a bit of an eye chart, but I just put it in there assuming you could download the PDFs later, I guess. This is from a DARPA study about infrastructure around the moon. It has big giant landers with masts for power and comms up here above the moon. Some go direct to Earth, some go through a relay satellite. You could be on the far side of the moon, and so you need that infrastructure in that case to go through relay satellites. Here's a company offering optical comms. That's good. We are good at generating lots of data, and we would like to be able to bring a lot of it down, etc. And so this talks about, different ranges of capabilities that'll be there. But we can leverage all these, these small little rovers or medium rovers to get us where we want to go. They're even talking about putting a railroad. Northrop Grumman is in charge of a study to put a railroad on the moon. Great, okay. I wanted to look at this over here. This is from this Aerospace Corporation, very recent report they put out. And they start with referencing a prior Aerospace Corporation report. But it goes through and just shows all these different things that you need to build up for the moon. And so starts with mobility and logistics and comms and PNT and power, et cetera. And so I put little blue arrows where we need those things, all the blue things we need, and we probably also want the things that are in yellow, like in situ resource utilization and space environmental monitoring, things that could disturb the system. And it's basically most of it. So we need to keep an eye on what happens with the development of all this, and a lot of it has commercial players doing a lot of the development. Some of it is not NASA supported, some of it is commercial. Here are the CLIPS landing sites. I got 2 more slides after this. And so it's a pretty active portfolio. The green ones here, here's Astrobotic. They did not land. They had a propulsion issue early in the mission on, not too long after launch. And then in the little purple boxes over here that are around, that's the contract value that's in the press release by NASA when the contract was awarded. So it tells you this is how much NASA is currently spending each mission that they have selected. And I'm looking at the numbers. There's no question that these original ones, and probably this one over here, and this one over here, probably those do not cover the full costs of the mission, and that those companies are relying on additional commercial revenues coming in order to make the business case complete. Nevertheless, you just kind of look, there's higher prices over here. If you just say $100 million class, it includes the rocket. This isn't just for the lander. This is the price NASA's paying to take stuff to the lunar surface. That's very important, because this is something that you could plausibly afford in an Explorer budget, especially if NASA Launch Services picks up most or all of that tab. Here is the larger lander, which has a CLIPS component in it, although it's essentially self-funded. So this is Jeff Bezos putting lots and lots of money into Blue Origin, and they're going to do their own 1 or 2 robotic uncrewed landers in order to prove out their system. But there's a lot going to the South Pole. There are many going equatorial. CS3, I think, is on here. This one here, Firefly, that's Blue Ghost 2. No, that's TO-19D. Where's Blue Ghost 2? I forget. Anyway, it's going to the far side. Schrodinger Basin is just around the far side towards -6 75 latitude, so it's quite south. But then there's one, this one over here. This is has a radio astronomy experiment on it called Lucy Night. And it is going essentially equatorial on the far side. So we're going everywhere, essentially, polar and in between. And so that means the capabilities for delivering the payloads have that capability. And we can go where we need to go. I personally will want to think about having direct communications with Earth because of our expected data volume. But you know, maybe there's a better place to go and you leverage more infrastructure. This is, on the other hand, what the Chinese are advertising. I like to show this because, look, they have a telescope with M31. All their depictions have that. They're putting telescopes on the moon. That's their plan. They also have a telescope looking at the Earth, and they have white papers talking about telescopes looking at the Earth to do certain science. They have big landers, they have hoppers, they have relay satellites, which are already in place. This looks like it's from a movie, or Roombas or something, but they have, you know, and this looks like Spirit and Opportunity. They have a diverse portfolio that they want to put down there, but scientists are driving a lot of what they're going to do. Does anyone know what DSL is? This is their recent selection for a mission that will fly. This is a 10 spacecraft free flyer in low lunar orbit, equatorial, to do the low frequency radio observations in basically the same kind of experiment as Lucy Night, but they're going to do it from orbit. 10 spacecraft in a train in lunar orbit, supposed to launch by the end of the decade. So a lot of science-oriented things that they're thinking about doing. And these are the folks that they're working with. The Aerospace Corporation report, which you can go look up, lists out what everybody's doing, all these landers and all the missions going, and you know, it's dozens of missions in addition to what the US is doing. And so everybody wants to go and have some role in these, and some will do it autonomously by themselves, like India will do additional landers with rovers, and others, I crossed out here with Pakistan. They just announced they're doing a rover on Chang'e 8, which is a 2028 sample return mission to the moon that's on China's manifest. Finally, I have this depiction. When Chandrayaan-3 landed, they had a hopper experiment. They fired up the engines, went up a little bit, and then came back down, just to see if they could do it so that they could figure out plumes and things like that. And so they had their camera. They were operating their camera during this experiment. There's a video there posted on X, which I decided not to try to embed in case it didn't work, but just showed before, nice and still, and you're sitting there looking at the surface, and then you turn on the engines, and you see the picture wandering all over the place, and all this dust is all over the place, and then when you're down, that's it, you're down. So the dust follows ballistic trajectories on the moon, and you learn a couple things here. First of all, landing is dusty, so stay covered up. That's going to be something we have to do. You can't land with apertures sitting out there exposed. You will get dusty. But once you're down, that dust on those ballistic trajectories, it settles very quickly. And then you're basically good to go. So the dust settles rapidly after landing, and then you can deploy and start your ops pretty fast. And then it's just a matter of making sure you're cognizant of the day-night protocols you want to follow, and dealing with the thermal challenges of being plus 200 and minus 200 C in the day-night schedule. So this is the total content that I had, and I'm happy to answer your questions. Thank you.